All right, welcome again, students, and this will be part 2 of oxidation numbers and their rules and how to use them and how to find them. So today we're just going to kind of quickly review some of the stuff that we learned yesterday. If you're wondering why my ugly mug is here, Michael Mays requested that, and so if you don't like it, you can complain to Michael. We're just going to give this a try. I don't know that it adds anything to the lecture or not, but whatever. All right, yesterday we talked about oxidation numbers. Again, this is probably a new concept and something new, so quick review. What are oxidation numbers? They're simply numbers that we use to describe the movement of electrons between atoms. So as electrons move from one atom to the other, either away or towards an atom, that's what we're describing. It could be in an ionic bond where there's transfer of electrons. It could be a situation like a covalent bond where you have a polar bond and those electrons are being shifted towards one direction or the other. That could be the situation. And we said we use positive oxidation numbers to illustrate that electrons have moved away from an atom, either shifting or transferring away. And then we use negative oxidation numbers to show that electrons have moved towards an atom, and whether that's moving towards because they're transferring to a nonmetal, or whether it's in a covalent bond where they're shifting towards a particular atom. So today what we're going to look at is we're going to look at, I think it's about 5 new rules. And the cool thing about these rules is these do not involve figuring out so much as these are almost kind of freebies, which is really cool when it comes to later on the tests and the assignments and things like that you will have to do. Because these kind of are, as long as you know this, then it's almost like free points. So these are rules really meant to help you. And we'll start with the first one. Rule number 4 deals with alkali metals, and that's what a lot of these rules do, is either they deal with a specific element or they deal with an entire family or group of elements, and they tell us, well, these are always this way. So for example, this first one, rule 4, and again a reminder, these rules are not in any particular order, so whether it's rule 4 or 5 or 20, doesn't matter what order it's in. The alkali metals, which is that first family on the periodic table, they have an oxidation number of +1 when bonded. And they are always bonded to something, so that's not really an issue. And so why would they have a +1 when bonded? Why would that always be the case? Well, they all have one valence electron, and being a metal, what are they going to do? That's right, they're going to lose that valence electron, which will give them a +1 charge. So if they have the +1 charge, then that means, if you go back to our rule we learned yesterday, +1 charge means that the oxidation number will be +1. And so that'll be true for every single alkali metal. So that makes our life a lot easier. Anytime we have a compound that has an alkali metal, I already know what the answer is for that. I don't need to search for it. I don't need to try to figure it out. I don't need to figure out the charge. I already know what the answer is. So that makes life easy. Rule 5 is very similar to it, and that is deals with the alkaline earth metals. And they have an oxidation number of +2 when bonded. And for a very similar reason, because the alkaline earth metals all have 2 valence electrons. Because they have 2 valence electrons, and being metals, they're going to lose those valence electrons, giving them a +2 charge. So we go back to the rule we learned yesterday, and that rule told us that, hey, if you have an ion, whatever its charge is, that will be its oxidation number. And so if its charge is always going to be +2, then its oxidation number is going to be +2 as well. So now I have 2 rules here, both the alkali metals and the alkaline earth metals. So I have over 10 elements in which are gimmes, basically freebies. I know exactly that every single time the oxidation number will be this. So that makes my life a lot easier. Now we're going to move to an individual element, and that is hydrogen. Hydrogen, generally speaking, always has an oxidation number of +1 whenever it's bonded to something, except if it's bonded to a metal. If it's bonded to a metal, we call it a metallic hydride, and then the oxidation number of hydrogen would be -1, but that's fairly rare. The majority of compounds that hydrogen forms, or that hydrogen would be involved in, it will be bonded with nonmetals, and so it would have an oxidation number of +1. And that has to do with its electronegativity. It has a lower electronegativity than all the other nonmetals, and so it would have an oxidation number of +1. those electrons would always shift away from hydrogen. And so that would cover probably at least 90% of the compounds that we would see with hydrogen in it. Very rarely are we going to see one where it's bonded to a metal. Every now and then that might be the case, but the majority of ones where we deal with hydrogen in this class, it will have an oxidation number of +1. And then rule 7 deals with oxygen. Oxygen always has an oxidation number of -2, so any compound that you see it, it will have an oxidation number of -2 with one exception, and that is when it's bonded to fluorine. And the reason that's the exception is because fluorine is more electronegative than oxygen, meaning fluorine will pull those electrons away in that polar bond away from oxygen. The electrons will shift away from oxygen. And that is the only exception. And so, again, this is like 99% of things that oxygen is bonded with, or you could say 99.9% of things that oxygen is bonded with, oxygen will always be -2. So again, this is another freebie, that pretty much anytime you see oxygen bonded, it'll be -2. So that's another freebie. And since oxygen is bonded to quite a few things, as we'll see here later in this chapter, a lot of the compounds that we draw, oxygen is often involved. And because of that, that'll really help you out knowing this, that oxygen's always -2. Last one today is rule number 8, and this again deals with another family. So we're covering 3 families on the periodic table that we're saying that this is always true about them, and this is the halogens. The halogens always have an oxidation number of -1 when they're bonded to metals. So we're talking about an ionic bond here, because you would have a metal bonded to a halogen. Halogens are nonmetals, and the reason here would again be because halogens have 7 valence electrons, and they're going to attract an electron, they're going to gain an electron, and when they do that, they'll have a charge of -1. So if we go back to our charge rule, whatever the charge is, that will also be its oxidation number. So the charge on halogens would always be -1 in an ionic bond. Now, what about if you had a halogen and it wasn't an ionic bond and it's a covalent bond? In that situation, then do the halogens have an oxidation number of -1? Sometimes. It depends, and what it depends on there is the electronegativity. Whichever one is more electronegative will end up with the negative oxidation number, and whichever nonmetal has the weaker electronegativity will end up with the positive oxidation number. And that's more something we're going to cover tomorrow in part 3, is how do you deal with covalent bonds. It's not quite as simple as ionic bonds, but it's still not too difficult. So we'll take a look at that tomorrow and deal with that at a later time. All right, let's look at some of the examples here that we have. And so I come down here and I'm going to write a little bit with this. All right, so here we are at the kind of the screen where we have some of our examples, and if you take a look, we have a variety of different examples, and these all incorporate the rules that we learned. Now, some of them we could simply use the rules we learned yesterday, but let's make it a little bit easier. So let's start with this first one here where we have lithium and sulfur. Now this is an ionic bond, so I could use what I learned yesterday and figure out, well, they're both ions, and so because they're both ions, as a result, then I could figure out their charges. But it's a lot easier. I know lithium's an alkali metal. Alkali metals are always +1, so the reality is I don't even need to figure out its charge. It's always +1, so I can just write that there. And then if I wanted to, I could figure out the charge of sulfur. There's no particular rule that applies to sulfur. Or if I wanted to set everything equal to 0, I could do that as well and come up with that sulfur, its oxidation number is -2. So that's one way I could do it. And again, the key thing is over here with lithium, it's how did I do it? Instead of finding out the charge of lithium, it was a lot simpler to just take a look and realize, hey, lithium's an alkali metal, they're always +1, so right away I already knew it. I come over here, there's actually 2 rules that apply here. It is an ionic bond, so I can find their charges if I want to do that. But again, it would be a lot simpler with calcium chloride simply to recognize this. Calcium is an alkali or alkaline earth metal, and we said that alkaline earth metals are always plus 2. And so right away I know that. I don't need to do any math. I don't need to figure out its charge. I don't need to worry about how many valence electrons it has. I already know that. It's always, all the alkaline earth metals are always positive 2. Chlorine over here, it's a halogen, and we said that anytime a halogen is bonded to a metal, then it's going to be -1. And so chlorine is -1. I don't need to figure out its charge. Now if I wanted to, I could, and I would find out that, hey, I get the same answer. If I wanted to set it equal to 0 and make an equation, I would find out that I would get the same answer. So there's the cool thing about oxidation numbers is there's a lot of different ways you can actually figure them out. Some are easier than others, but you will end up with the same answer any way you do it. So that's kind of cool. If you forget one way, there's always another way that you can approach it. And that's kind of the awesome thing about this. I come over here with hydrogen and oxygen, water, H2O. Well, I know that hydrogen is always +1, except when it's bonded to a metal. Oxygen is not a metal, so I come over here, and I know that hydrogen's +1. And I know that oxygen, we said, has a rule that applies to it. It's always -2. And so right away, again, I know both of those. And so again, things like this end up being freebies. If I had a compound like that on the test, I shouldn't even have to put any real thought into it. Hydrogen +1, boom, I've got that answer. Oxygen -2, boom, I've got that answer. Those are 2 freebies, free points, in essence, right there, if I know how to apply these rules. All right, this one down here. Chromium. Now this would be a situation where you actually do have to use a couple different rules, and so I take a look at this. Chromium I know is a metal. I know this is an ionic bond here. I don't know what chromium is though. I don't know how many valence electrons it has off the top of my head because it's a transition metal. We said transition metals are unique. I do know oxygen, however, and I know that oxygen is always -2. Okay, that's its oxidation number. And so then I can use my little equation that we said we know the sum of everything has to equal 0. So I can set up my equation X for chromium. I don't know what its value is. The sum of the oxidation number, so sum means add. And my oxidation number for oxygen is -2. Has to be equal to, we said, 0. And so I can set up my equation, solve for chromium, and when I solve there, I find out that X equals 2. And so chromium there has an oxidation number of +2, and oxygen is -2. It's so simple like that. So I can use it to solve some of those equations. If I take a look at this last one over here. Now this one's a covalent bond. So it's not an ionic bond. I don't have charges. And this one works a little bit differently. Being a covalent bond, it's not about finding the charges. I'm not going to worry about, oh, well, phosphorus has 5 valence electrons, and so it's missing 3, so it's going to have a charge of -3. No, that's not the case because it's not an ionic bond. It doesn't have a charge. But what I do know is oxygen's always -2. So how do I find what phosphorus is? Well, I set up my equation. I have 2 phosphorus. I don't know what they are, so that's going to be X, so 2X. It's the sum of, so plus, I have 5 oxygens, and each of those oxygens has an oxidation number of -2, and the whole thing has to be equal to, my compound always has to be equal to 0, and then I can go about solving it, and if I took it step by step, I have 2x minus 10 equals 0, and then if I moved everything over to the other side, I would end up with x equals 5. And that would be my answer for phosphorus. Phosphorus would be +5, and I'm good. So that's the way that we would apply these. We'll have some practice in class tomorrow, and that is the end of our lecture today.